Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on Richardson extrapolation. And as we mentioned before, Richardson extrapolation is a very clever trick to accelerate the convergence of an approximation for a given function. The idea again is that we do not know the expression for f of t, so we cannot evaluate it, but we know an approximation, a of t and h, which evaluates at the point t that we are trying to find the function at, but it also depends on another parameter h, and h is typically representing our error, which means that as h gets smaller and smaller, we expect the approximation to become more and more accurate. And two obvious examples that are also very important are differentiation, f prime of t. If we want to numerically calculate the f prime of t, we calculate it as f of t plus h minus f of t over h, where h goes to 0 eventually. And we know that for this simple forward approximation, the error is linear in h, right? h squared, etc. For integration, if we define an integral function, so a from a to t, a is fixed, t is varying, we can approximate it using a forward rectangular approximation or backward or center or trapezoid, Simpson, any type of method that we discussed in the past. And what happens here is that for a forward rectangular approximation, h and the number of subintervals are related. Basically h here becomes the length of each subinterval, and as the h gets smaller and smaller, n gets larger and larger, and then we get smaller errors. But the problem is that sometimes we do not want the h to get smaller, because in general, for example, in case of differentiation or integration, if the error is just linear in h, the order of error is 1, h to the 1. Then if I want to reduce the error by 1 order of magnitude, I have to reduce h by 1 order of magnitude. And that for differentiation, that requires calculating the f at a point very close to t and then dividing it by a very small number. And sometimes it causes some errors, okay? Similarly, in the integration, if I reduce h by 1 order of magnitude, it means I'm increasing the number of subintervals with 1 order of magnitude, and that causes to some many more number of terms here, more evaluations of the function, and if the evaluation of the function is costly, then it's just going to have a huge impact or computation cost. And we said that what we can do, we can use a very clever trick, is that instead of dividing h by 10, reducing by order of magnitude, just reduce it by a factor of 2. And then try to multiply by 2 to the m and subtract the 2 terms, and we ended up with this new approximation for f. And we said that as h goes to 0, this new approximation also gets more and more accurate. But the difference here is that this new approximation actually has an error. The leading term of the error is has one order of magnitude better than the previous or the original error, which was h to the m. Now this one is h to the m plus 1. And then we said that this is a very good point, because then we can do a recursion. If this is an approximation based on the previous approximation, we can continue this cycle. So the next approximation is based on the new approximation, and the next one after that is based on the previous approximations. And we get this thing, and this one helps us after basically n approximations. The order of error goes from h to the m to h to the m plus 1, m plus n. So we increase the the order of magnitude by this kind of recursion. And what it takes is that we just divide h by a factor of 2 in each recursion. So if a0 is the original approximation, a1 requires calculating of the h, a0 at h over 2, a2 requires the calculation of a1 at h over 2, which means we have to calculate the original approximation at h over 4, okay? Now this is very interesting, because now if we reduce h by a factor of 8, which means dividing it 3 times. It's like doing this recursion 3 times. So instead of reducing the error by 1 order of magnitude, we in fact reduce the error by 3 orders of magnitude, which is a huge deal, all right? And then we said that we can also do a very simple approximation of what the order of magnitude of the error is. Sometimes we don't know that. And in order to do that, we just take like h over 2 and h over 3 and make them equal. The first recursion term equal to each other, and from that we can solve for m here. And we said that basically this type of method is can be generalized for any sequence that converges to a number a, and from this we can create a new sequence. And if the limit of bn minus a over an minus a when n goes to infinity becomes 0, it means bn has a faster convergence to a than an. And we will look into this in the future of what are the topics or what are the different methods that we can construct a new sequence from an old sequence. And this is especially useful when we're dealing with infinite series that sum over infinite number of sequence terms, okay? And then in terms of implementing in Java, we said that, okay, we start with the functional interface. Let's call it Richardson function, and it depends on 2 variables. The first one is based on our notation is the t, where we actually calculate the function at, and h is our error variable. And then we define a class that implements this Richardson extrapolation. So let's head back to Eclipse and try to implement this. So here I have the Richardson function interface. It just has one public abstract method, which is a value, and it evaluates the function at based on 2 variables, var1 and var2. var1 is t, var2 and h. And in the Richardson extrapolation class, I have a private Richardson function and initial order, which is defaulted to 1. So I set it as a default 1 because this is the worst case that can happen, right? In any type of approximating a derivative or integral, typically the worst case is just 1, right? Linear error. And then in the constructor, we just set the function and also pass in the initial order, all right? And obviously we can have also a constructor that does not have an initial order. If it doesn't, we just default it to 1. Okay. And then we can have a method for setting the Richardson function, a method for setting the initial order. And then here I have the method called iterate. And in this method, what I'm going to do, I pass in the t, the point that we are calculating the function at, and then the h, which represents our error parameter, and then int t, for which means how many times are we going to do this Richardson recursion, right? Remember, n here represents the this here. So we're doing, so here if k is 0, we are doing 1 iteration, right? a1 equals a0, 2 to the m a0 minus a0 over 2 to the m minus 1, which is the first iteration, right? If k is 2, basically, so the index here is n, right? If an represents our sequence, a0 is the original one, a1 is the new one, a2 is the second iteration or second approximation based on a1, all right? So this is how we're doing this recursion, and each time it increases the order of error by 1 order of magnitude. So what I'm going to do here, I don't want to change the original Richardson function. So what I do, I make a copy, func copy of type Richardson function, and then for int I equals 0, I less than n, I plus plus, I write a method next. And this next method takes the func copy and iterated over the for loop, right? So we start, if n is 0, we do not go into this for loop, and just the func copy is the original copy, the original function, which is the 0th term of the sequence, and then we evaluate it at t and h. If n is 1, we want to get the first Richardson iteration, so I from 0 to less than 1, which means I is only 0, and func copy becomes next func copy and I is 0. Alright, so this is how we're doing iteration. So what is this iteration? So this next obviously must return a Richardson function, and this next basically takes a Richardson function and the order, okay, and this order basically is the order of sequence. So order is the order of sequence or recursion. So it starts from 0, 1, 2, 3, etc. Alright, and this m is basically what goes here in this power, and if you recall, it's m plus k. So order in this case is basically representing k, right? So if order is 0, we are evaluating k1, basically we are evaluating a1, etc. Okay, so the power that we calculate, we have a 2 to the some power, and that power is the initial order plus the order of recursion, and we calculated it, and then the new Richardson extrapolation, the new term for the sequence is still an approximation, so it should be a Richardson function again, right? So var1 and var2 go to coef, which is 2 to the power, times the value of the current function at var1, which is our t, and half of var2, this is h over 2, minus the value of the func at var1 var2, okay, divided by coef minus 1, and it's exactly this term, right? And we repeat it as many times as we want based on the order that the user specifies in terms of the recursion order. So each time we repeat, we return a new Richardson function, and then eventually we evaluate it at t and h, okay? Alright, so I already have created a test Richardson here. I have two tests. Test 1 is basically what happens in test 1. I create a function and I'm using the standard function interface, a standard function interface in Java, which takes a double and returns a double, okay? So T and R. T is the type of the input, R is the type of the result, alright? Input is double, return type is double. T goes to T squared. So my function here, basically f of x is x squared, and the goal here is to calculate the derivative, and we already know the exact result. 2x is f prime, all right? But then I'm going to, so I create a Richardson function, var1 var2. It takes var1 plus var2. This is f of x, t plus h, or x plus h minus f of x, sorry. So var2 is h, var1 is x or t. So x plus h minus f of x divided by h, var2. This is our standard forward approximation. And then what I'm doing here, I'm trying to calculate this derivative at x equals 1 or t equals 1, okay? And based on different h. So each time I reduce h by, I start from point 1 and reduce the h by 1 order of magnitude, 10 to the ith, and I goes from 0 to 4, okay? So it's 0.1, 0.01, 0.001, etc. All right. So now let's run test 1. This is to just show you that the error is in fact linear in h. So if h is 0.1, the simple case, this is this naive or simple approximation of the derivative, is 2.1, and the exact, remember, is 2. And then if h goes down by 1 order of magnitude, h becomes 0.01. The error also goes down by 1 order of magnitude, 0.01, okay? So we get 2.01. So the error was 0.1 here the error is 0.01, okay? Now maybe let's multiply by another factor 2 so that I show you that it's actually the error. So the exact is 4, we're getting 4.2, 4.02, and if h goes down again by 1 order of magnitude, the error also goes down by 1 order of magnitude, 0.002, etc. Okay, so this shows that the error of this approximation for the derivative, the forward approximation, is in fact linear in h. Now let's look at how Richardson can absolutely crush this and give us a very exact result, very accurate result just by one iteration, like absolutely crushes it. So we're going to do 2 times t squared, so we have 2x squared, and the exact value should be 4x. So I again have my function, t goes to 2t squared, and the derivative, I create the Richardson function exactly based on the forward approximation, and then I create a Richardson extrapolation and pass my Richardson function and the order 1, okay? And this is based on the assumptions I already know the order of error for this function, which is 1. If you don't know, you just can pass 1, because 1 could be just the worst case that could happen. And then I set h to 0.1. So h is always fixed at 0.1, but then I'm going to iterate over the recursion for the Richardson. So what I'm going to say that, okay, I goes from 0 to 5, from 0 to 4 actually, and then in the iteration I'm going to get the Richardson extrapolation dot iterate at t equals 1, so x equals 1, we can, and based on the edge. So h here is fixed, unlike the previous example, but then the I is changing, the order of recursion is changing. So obviously when I is 0, we get exactly the same result as before, right? Because the Richardson functions are the same. But then when I becomes 1, our error should reduce. And here you will see that not only it reduces by a factor of, it doesn't just increase by an order of magnitude, it actually increases by more than that. So the first, when h is 0.01, basically in iteration 0 we get exactly 4.2, but then in the next one we pretty much get the exact result, 3.999, which is 4, and then after that it's basically constant, it's just 4. So after one iteration it absolutely crushes the original approximation and gives us exact result. So this is really the power of Richardson approximation, and we can do this for more complex functions. For example, let's change this to, I don't know, math.sine of t, and then let's evaluate it at 0. So we already know that the result should be 1, because derivative of sine is cosine, and then it calculates at 1. So let's see. So it gives us a relatively good approximation, 0.99983, and each time the error increases. And as you can see here, this forward error in fact has a each time when we reduce the error by 1 order of magnitude, when we reduce h by 1 order of magnitude, the error goes down by 2 orders of magnitude. That's because if you look at the Taylor series of sine, it's basically x minus x cubed over 6, right? So there is no x squared term. That's why when you write this forward approximation and use the Taylor expansion, you end up with h basically cubed, not h h or h squared, and you end up with h cubed, but then you divide it by h, you end up with h squared. So the order here is in fact h squared, not h. So the order could in fact also depend on the function, but in general, regardless of the function, the worst case of error for this approximation could be 1, h or h squared, could be h. But for special functions like sine, it could actually in fact be h squared. Now let's see what happens to our Richardson. So as you can see, in iteration 0 we get exactly the same result, but in iteration 1 we get 1.000836, and in iteration 2 we pretty much get the exact result, And as you probably can see, here in this case, Richardson and our approximations are pretty much similar. That's because I set this to 1. I assume that it's 1, but in fact it's 2, right? For the sine, the order of error is in fact 2. So let's see what happens. Now it has a faster convergence that so this gives us 4 nines, this gives us 6 nines. 1, 2, 3, 4, 5, 6. So it's basically giving us this. And then we get exact result. All right. So 1 or 2. So if the order of approximation could in fact depend on the function, but in general we can just consider it to be 1 and then do 2, 3 approximations or 2, 3 recursion iterations on the function. Now what I'm going to do here, I'm going to go back to Richardson approximation and try to let me just remove this. What I'm going to do here, I'm going to implement this method, estimate initial order, and in the estimate initial order, what we are going to do, we're going to use first iteration, okay? And in the first iteration, we're going to put this at t. So we're going to pass in t and then double h. So based on the evaluation point and h, the error factor or this error variable, we can approximate the initial order. And remember, in this example, sine has a Taylor expansion of x minus x cubed over 6 around 0. So around 0, when the evaluating point is 0, the order of this forward approximation for the derivative is h squared. But if we evaluate it at any other point, let's say 1, then it does, in fact, when you look at the Taylor expansion, it does have an x squared term, and then you get h squared, and then divided by h, you get h. So the order of error becomes 1 instead of 2. So let's try that. We do have some, so let's comment this out. Let's run this. Now as you can see, the error, the forward approximation does, in fact, it doesn't look like a quadratic error reduction. It's more like a simple linear error reduction. And then in the Richardson, so I'm going to put this also as 1. So in the Richardson, the first term is the same. Second one is 0.54. We get 0.536, so we get better approximation. And then we get 0.5398 with 54, and it basically gives us a very accurate result. And remember, although the results of the simple approximation seem to look accurate, but remember, and this comparison is not fair, because in the Richardson we are dividing h by 2. So at the beginning it's h, and then h over 2, h over 4, h over 8. So iteration 3 we haven't even reached h over 10, which means this term. So we have to in fact compare this term h 0.01, which is 1 order of magnitude reduction, with this term, which is basically the exact result, almost exact result. So that's how we actually should compare the Richardson with the simple approximation, with the naive approximation, okay? And all right, let's go back to the Richardson and try to implement this function. So we're going to use the first iteration, basically h over 2 and h over 3. So what we're going to do here, we're going to get a Richardson function. We're going to get func1, And then so what I'm going to do here, so if I go back here in the slides, we have the original Richardson function, a of t and h, and then we have to substitute h over 2 and h over 3. All right, so as you can see, we have h over 2, h over 3, and h. So let's evaluate this. Double half h term, maybe term half h, and then double term. This is ta, which is func dot value at t and h. Okay, and then half h is func dot value at t and half h. Okay, and then double term 1/3 h is func dot value at t and h over 3. Maybe let's just write this also at h over 2. Okay, now we have these terms and we're looking solve for m, which is our initial order. And in order to do that, I'm going to have double arg1, which is basically let's go back here. It's half h minus half h minus third, so double term half h minus term 1/3. Okay, and then double arg2 is term half h minus term, and double arg3 is term 1/3 h minus term. Okay, so basically I calculate it, I brought this to the left side, I calculate this, and I calculate this one and this one, and now I have to solve my equation. And the equation is something like this. So in order to do that, in our demo, where is our root finding package project? So these are our, so we have to create a we have to create a real root function. Okay, so let's give it a dependency. Let's go to the build path, and here on the projects we're going to add the demo roots. Okay, and then I'm going to create a real root function and root func, let's call this, and this takes m and returns basically arg1, okay, minus arg2 over math.pow2 to the m minus 1, and minus arg3 divided the math.pow2 to the m, or 3 to the m minus 1. All right, and then we're going to create a real root. We'll call it root finder, new real root, and pass in our root function. Okay, and then we're going to return or double m equals root finder dot we can do any type of method. Let's try Brent, for example, and or maybe let's start with the bisection. Let's go, let's say m is between 0 and 100, and then we're going to return m. And remember, this m is we're returning as a double value. We can cast it to int, but first let's try and go and test it. So in the test Richardson, I'm going to create a new test 3. All right, and in the test 3, I basically am going to actually, let's put this on top, and another one on top of that. Test 3. In the test 3, I create my function. This is the derivative sine. I'm going to this is my edge, and then let's try to sys out on the extrapolation. Estimate initial order. T is, let's say at 0, I wanna estimate the initial order. So let's see. It returns a none, so it cannot find. Let's see at 1. It still returns a none, so apparently there is no solution here. Let's go back. So we calculate the half h minus the third here, and plus this one, half minus a over 2 to the m minus 1. Half term minus term, 1/3 minus term. So arg1 minus, oh, actually this should be plus. Let's try it again. It still returns none, so apparently it's not able to find it. Now what we can do here, I can actually, let's try to plot this function. Let's try plotting to see how it behaves. Double mvals equals mathutils dot, let's also give it a dependency on the math library, mathlib. Mathlib.linspace from 0 to 100 point. Double yvals is array func dot apply. Basically m goes to root func dot value at m, apply to mvals, and MATLAB chart, fig new MATLAB chart, fig.plot mvals and yvals, and fig.render plot, fig.show with a true flag. Alright, so let's see what happens here. And we have to go in because I'm running this on Mac, I have to remove this check. Okay, so the function does in fact cross the 0 at exactly 1, right? So it's actually better than 1. It's between 1 and 105 as expected. Now the question is, why is it that our root finder cannot find it? Because definitely there is a bracket around the root, and so the root finder should have absolutely no problem finding it. So we are saying that root finder from 0 to 100. Okay, that's odd. Let's try another method. For example, trisection. 0 to 100. Okay, I'm going to also set the After I render it, set the font size to 13 to just make it easier. So let's run the test. Okay, so bisection cannot find it. Again, it's a little bit strange why it's not able to find this root. Let's try another method. Trisection. I'm going to use PSO. 0 to 100. Let's have a quick look at this PSO. We create a PSO, set minimize true, solve for 100, and then best position at, okay, so let's try PSO. Root finding based on the PSO. It still returns a nan. Okay, I guess that's because, okay, so I shouldn't put 0 here exactly, because at 0 it blows up. So let's put 1 in negative, let's just say 0.1, so it does not blow up. Okay, it still returns a nan, which is very odd. We should get a 1. It's very strange that we are not able to find it. Let's try another method maybe. So let's try Brent from 0.1 to 100. I guess this requires that we do have a bracket around the root in minus 6 e to the 16, so definitely it's not able to find it. And now it's still strange because we do have a bracket around 0, so let me see why this is not working. So bisection should be able to definitely work. Bisection double start, which is 0.1, and let's say 100. Oh, okay, now it's able to find it. So bisection should be able to find it, no problem. And we're getting, as expected, we're getting 1.02245. So the order is very, very close to 1, as expected. Okay, and you can clearly see here where the function is crossing the horizontal axis. Now what happens if I set this to 0, for example? We should get, in fact, something close to 2. Yes, we get 1.99992589. Okay, and that's because, again, because of the Taylor expansion of the function at 0, we don't have the h squared term, we get t cubed, right? That results in, when you evaluate the numerator, you get h cubed, and then divided by h is h squared. So the error is, in fact, h squared. Here, almost exactly 2. So what I'm going to do here, if we invoke the constructor with no function, with no initial order, I'm going to call this method. And the problem is that, okay, so then the problem is that here, all right, so let's set this to 0. We're going to initialize if no initial order is given, we set it to 0, and then when we set it to 0, we here in the iterate we check if the order is given, check if the order is given, if the error order is given. If initial order is equals to 0, just call the method initial order equals get estimate initial order at t and h. And then the problem here is that the initial order, let's just make it double, no need to make it integer. It automatically does the casting here, so let's also make this double. There's no need for the order to be integer, and then we apply 0 here. And then the problem here is that let's also make this double, but then the order of iteration we definitely want to it to be integer, so no problem there. And then math.abs initial order is less than 1e negative 10, for example. For doubles, it's always recommended to use a tolerance for comparing to, for example, 0 here. And then compute Richardson iterations. Okay, and maybe let's also make these package level access, the Richardson function. And then all right, so we are good. So as you can see, depending on where we evaluate the function at, we can get the order of the error can change, and that's a good thing, because now we can in fact let's also not pass 1 here. As you can see, it returns 2. And let's try another function, for example cosine. The Taylor expansion of cosine is 1 minus x over 2 over 2, okay, at 0, and then we get h squared in the numerator, and then when you divide it by h, we get h. So the order at 0 should be linear instead of quadratic. So let's test that. Yes, we get 0.99822889. So the order of error is in fact 1. Where it crosses the horizontal axis, it's pretty much 1. Okay? Now be careful, if you cast this to an integer, you get 0, you don't get 1. So you have to be careful, and that's why I kept it as a double value instead of linear. So I'm going to comment this out because I don't want to plot this. And then so the other thing is that the initial order, basically here we're saying that each time you calculate the initial, it only calculates the initial order once based on whether or not it's 0. So maybe it's better to just always calculate the order. So based on where we calculate the t, we estimate the initial order and then do the iteration on Richardson. Okay, now the problem here is that obviously if we call this method multiple times, we're going to, or at different t's, for example, if you want to find the derivative function at different t's, then we calculate the order each time, which is probably not a good idea. But in general, it's better to do it like this. Find the order and then calculate it. Okay, I'm going to put this, bring this back. So if initial order is not set, we just use the initial order here. And for cosine at 0, it's x squared over 2, so it should be linear. At other points, so cosine, let's say at math.pi over 2, it's 2, right? So when cosine becomes 0, the order of error becomes 2. And we can in fact plot the order of error. So double order, or basically double the t-vals, new or math utils dot linspace from let's say from 0 to math dot pi and 1000 points, and double error order equals array func dot apply. Our real function is that t goes to basically extrapolation dot estimate order at t and h, and we're going to apply it to t-vals, and then we're going to do a plot here. So let's just go here and copy all this code, create a MATLAB chart, fig, plot t-vals and error order. Let's import this. All right, let's see. Yeah, so what we see here is that let's see what we have here. So the error order when t becomes basically pi over 2, the error order goes up and goes down. So we have some sort of discontinuity here. But in general the error order should remain around 1 because of the fact that in general this forward approximation should give you an error order of 1, and we can basically see it here, right? Just around this this 0. Let me maybe reduce the number of points. We still have this discontinuity here. Okay, run it with more points, and yeah, so at 0 it's 1, and okay, error order t and h, t-vals. Okay, so basically the error should be around 1, and if I change this, let's go and back to sine. Let's see what happens now. Yeah, so at sine, basically what happens here is that at 0 is 2, and then error comes around 1 as expected, and then goes to about 0 at pi. When the function, the sine becomes 0, the estimated error is not well behaved, but we can still assume that it's 1. Alright, so this was the idea behind Richardson Extrapolation. It's a very powerful tool, and I hope you enjoyed this video, and I'll see you in the next video.